Hello and welcome to another Babble video with myself, Deepak on Tech. Today we're going to take a little look at the kind of low-level operation of the Apple II. I just happen to have an Apple IIc here. It's turned off, hence no signal. Don't worry, you're going to see some things in just a moment. And I think these vintage machines, these 8-bit computers, they're very, very interesting. They provide you a lot of very low-level access to the hardware in a way that's not really easily possible in the present day, and you can learn quite a lot about computers and programming and their operation by playing around with these machines, I think. So I think it's very much worthwhile preserving these machines and the knowledge around them. So I thought I don't have much of a script for this one, to be honest. I thought I'd just chew off some bits and bobs with regards to the operation of the Apple II. Because I think it is kind of cool, and I think it is important to preserve these things. And there aren't really, there are many sources, but it tends to be like scanned PDFs and things like that. It takes a bit of time to pull together all of this information. I'm sure there are lots of smart people out there who already know all of these things, but it took me a while to track all of this information down in any case. So anyway, let's go ahead and power our machine on. I've got an Apple IIc here. It's a late model memory card version of the Apple IIc, as you can see, as it says in its boot screen, Apple IIc there. I've just booted it up without a disk in because the ROM on the Apple II actually has quite a lot of stuff built in. So I'm just going to quickly first demonstrate what you get just on the ROM without even putting a disk in the drive. And then we'll move on to actually booting ProDOS, which is what you would tend to use as your operating system with this particular type of machine. So yeah, don't have a disk in, so it says check disk drive. If I hit Control Reset, it's going to beep at us, and then we get a right square bracket prompt. Now this is an Applesoft BASIC prompt. Earlier Apples might have had integer BASIC, and even earlier ones would have actually booted straight into what's called the machine language monitor, which this machine also has. We're going to cover that in a moment. So even earlier machines didn't even have BASIC, but here we are. We're at a BASIC prompt, and we can do all the kind of usual things you would expect. So I can run a print command, and if I do it without a line number, we're in a kind of immediate mode, and it will execute the command straight away. Or alternatively, as always, we can use line numbers. So we can type in some stuff for later execution. We can list it, and it will show us kind of what's currently sitting there in memory. We can even give it a range. If we had more lines, of course, that would make more sense, but you can actually just pull certain lines out of the listing as well. And then if we want to, we can issue run, and the command will run. Control C, just like with a modern computer, will break the program, and it'll even tell you what line number it was on when it broke. So there we go. We got a break on line 10, sorry. If we'd had a syntax error or anything like that, we could list straight to that line number and figure out what is going on. New command blanks out the current program. So you can see list is telling us there's nothing there. And home is kind of the Applesoft BASIC equivalent to CLS in DOS. And there's not really that much more that we have here. We can type basic commands directly for immediate execution. We can enter line numbered bits of code, and they'll be stored in memory, and so on. But we can't. We've got no disk operating system right now, so I can't. Cat is the normal command for cataloging a disk in ProDOS. I can't create new files. I can't delete. Like, all of that kind of usual stuff is simply missing at this point. We've booted straight from the ROM, and the system has no access to any drives in the system. So we can do this. Call -151 or -151. And that puts us into an asterisk prompt. Now, this asterisk prompt is the machine language monitor. This is a very, very nice facility built into the ROM. This allows us to do a lot of different stuff, primarily taking a look at memory locations in the machine. The Apple II is a memory addressed system, as many computers are, and so pretty much everything in the system is mapped to a memory address. And we have memory addresses that represent the RAM, the ROM, the frame buffer, which on a machine like this is actually just in RAM, and various other things. We can have stored routines at memory locations, and we can access those, and even hardware can be accessed in a memory mapped fashion. So you get a lot of power here. Now, usually when you're writing programs, you're starting at memory location 0300. This is all in hex, by the way. So if I enter a memory location in 4-digit hex and I press enter, it's immediately going to tell me what is in that location. So currently it's telling me that that location contains FF. Now, if I supply a dot separated range of addresses, it's going to tell me what's inside all of those. And you can see currently we've got FF in all of those. So, these are basically blanked out. There's nothing really going on in any of these. I could poke things into these various addresses and see the results. And if the things that I poke into there happen to be assembly or machine language, they are executable, which is kind of cool. So check this out. If I enter a memory address, and by the way, we can actually enter memory addresses without the leading 0. We can actually do it kind of like that. If I do a colon and then I start typing in data, that will be stored at that location. So I'm going to enter A905. And what that does is it loads the accumulator. If you know your opcodes, opcode A9 is actually, let me see if I can remember now, LDA, which is load to accumulator, and then 05 is simply the hexadecimal value I've given it. So that would load the number 5 into the accumulator, and then I'm going to store it. So that was 2 bits that I gave, by the way, so that was 300 and 301. So my next instruction needs to come at 302. And for this one, it's actually a 3-byte instruction. So we have the opcode 8D, which is to store the accumulator to a memory address. And then we're going to type in the memory address OF03. Now, note that the Apple II is little endian, so these are kind of reversed. This is actually memory address 030F, but we type it kind of backwards. So we can do that. Now that was 3 bits. That was 302, 303, and 304. So my next one needs to be 305. And we're simply going to issue RTS, which is return to subroutine. That's effectively like a quit. So if I was now to list 300 to 305, I'm going to get our entire program in machine language. And here we get a nice little trick that the machine language monitor has. Let's type 300L. And that's us telling it to show us 16 addresses, but with decoding. So you can see on the left-hand side is my original code that I entered, and on the right-hand side it's decoded it. So LDA for load, and then anything that begins with a hash is an actual value, like a direct value, basically, rather than an address. Normally you're supplying memory addresses, but that's an absolute value. So absolute value, $symbol means it's in hex. So absolute hexadecimal 05, and then I'm doing a store accumulator, STA, to just dollar, and then some numbers, so that's a memory address, and then RTS basically says, hey, I'm done. We can return. So I could now do 300G for go, and that will actually run the program. Okay. Program is run. How do I know that the program worked? Well, 030F should now contain 5, and it does. There you go. Very, very simplistic. So that's the machine language monitor there. The other thing we have, I had to memorize opcodes there, which is not the way you're normally going to want to work with assembly. Actually, you're probably not going to want to work like this at all. You probably want to use an actual proper, fully featured editor with a built-in assembler like Merlin. Or actually develop your software completely off of the machine. But we do have this thing called the mini assembler. We can type exclamation mark and press enter, and you'll see that we now have the exclamation mark prompt, and this lets us know that we're in the mini assembler. So, and in the mini assembler, I can simply press enter, and it takes me back to the machine language monitor. There we go. And I can, as before, I can type in addresses. Oops. In fact, we can't do that from in here. The mini assembler is more for actually building your program. So let's go into the mini assembler and let's actually build a program here. Now, rather than doing opcodes, I can now actually type the assembler commands that I want to use. So this has a bit more functionality. So let's start with, let's load the accumulator. We'll give it a value. Let's actually do the same program just now. Load 05, boom, we're done. That's great. And rather than having to type a memory address, I can now actually just type the commands directly. So we're just going to store the accumulator. Let's go 030A this time. Didn't like that. Didn't like that. So that was 2 bits, so we should be at 303. Oh, do I have to... Actually, I think I know what I did wrong. Note, by the way, if you're used to more modern machines, backspace just creates a character on the screen. You have to use the left arrow to go back to where you want to actually edit, and then just start typing, and it will effectively overwrite. It won't submit anything to the right-hand side of your cursor, so you don't need to worry too much about leaving garbage on the screen, although in this case we haven't. Yeah, it also doesn't work. I need to know my memory addresses. Okay, fair enough. Well, anyway, next one would be 303. And we're going to do 0308. Boom, there we go. And you can see we've got our 2 lines are showing up on the screen there. And then that was 3 bytes. So our next command is 333435. So we need 306 now. And we're now going to do RTS. So you can see this makes our lives a little bit easier. We now hit enter and go back to the machine language monitor. We're going to do 300L, and it's going to print out what we actually have. Ooh, I skipped a bit there. So that's probably going to crash, actually. But we can edit that from in here very quickly. We're going to do opcode 60 in there. 300L, and yep, there you go. We just got 2 RTSs, one after another. That's not going to matter. Okay, and again, we could run that program. And then if we take a little look at what's in memory, store it. Oh, OA8D is where it ended up putting stuff. Okay, interesting. OA8D. Let's see. DB. Okay, I'm assuming that's a funny area of memory that we can't actually write to. So we'll not worry too much about that. In any case, if I now do Control-C and press Enter, we drop back to the basic prompt. So we're now back in our normal environment. And the cool thing about this is if we'd had a basic program, it doesn't clobber it. So you can actually work in Machine Language Monitor and in BASIC all at the same time. So next, let's see what we get if we actually boot from a ProDOS disk. I'm going to press Open Apple, Control, and Reset. The machine will reboot, and it's now going to see what's in the disk drive. So everything you saw before was in the ROM. That's just built in directly to the computer. We're now actually booting an operating system, in this case, ProDOS 2.4.3. And after a little bit of a delay, we're going to get what basically looks like the same prompt again. We've got the right-hand square bracket. We're back at a basic prompt, but we now have ProDOS commands loaded into the system as well. So we can now issue disk operating system commands like cat, and here we go. We actually get a listing of what's on the drive. And you can see that there's not very much on here. I literally just have ProDOS itself and then basic.system. So that gives us access to all our bits and bobs. You know, we could now create a file, operate with files on the disk, which is nice. But the good thing about this from a programming point of view is we can now actually store our programs on the disk, which is, you know, kind of a good thing to be able to do. Previously, everything that we entered was sitting in RAM, and of course, as soon as we powered the machine off, we would have lost it. So, you know, that's going to be a waste of effort if you end up creating a whole bunch of programs and then, you know, you don't have any way of actually saving them. I'm going to put in a different disk now. You know, all of this is now in memory, so I don't actually need to leave the operating system disk in. And I'm putting a different disk in the drive, which just happens to have a bunch of programs and bits and bobs in it. And we're then going to demonstrate some of what you can do now that you have access to a disk operating system. So I'm going to make sure that my basic kind of buffer is empty by typing new. I'm going to clear the screen with home. And now we're going to make some kind of a simple, very, very simple program here. So I'm going to go ahead and print hello. And that's basically the end of the program. I don't think we need to do anything after that. Do a break after that. And we can now issue a save command. We have access to that. We didn't before. So we can say save hello. If I go ahead and do that, we're going to end up with a file on the disk. If I cat that now, you should see that we have hello, and it's of type BAS for basic. That's great. And now, even if I blank out my basic buffer by saying new, I can now issue the load command and load hello back into memory. I can list it. There it is. I can run it. And we got a syntax error at 20. There's no such command as break. So I don't actually know what I'm doing with the Applesoft BASIC too well thus so far. Now, what you'll notice is we actually have a bunch of binary files in there as well. These are a lot of fun. You can do some cool stuff with these. So actually, let's, for just a moment, let's switch to 80 columns mode and run the catalog command. Now, catalog is the same as cat, but designed for the 80 column display, and it gives you a bit more information. And you'll see that these binary files have a subtype A equals on them. And that tells us what memory location they're going to get loaded into. And you can see that a bunch of these have 0300, just like we were demonstrating before. So let's take high. So we have a series of commands just like the basic ones beginning with B, which stands for binary. So a binary load, binary save, binary run. I'm going to B load the high binary, and it's going to put it into memory location 300. I can now, as I did before, call 151, and I can now say 300L and give me the decode of that program. And you can see that it does a few different things. We're doing some load, some store, some load, some store, and then an RTS. I think there's some nonsense commands after the RTS that I left in from a previous program. So in any case, if I do 300G here, it's going to run the program. Oh, and actually, it printed some nonsense characters to the screen because this program is designed for 40 column mode, and I'm now in 80 column mode, and the character map is different. So I'm going to Control C, enter, and I'm going to do Control reset and run home. That puts me back into 40 column mode. Okay, so if I go back into the machine monitor, let's take a little look at the memory. Yep, the memory is still here. It didn't blank it. I can now do 300G, and it gives me flashing high, and that's what it was supposed to do. If I drop back to the basic prompt here, I can also do brun. Oh, but I need to tell it what I'm running. I can brun high. It will load it into memory and immediately execute it. There we go. We got another high. So that's working nicely. The same command for kind of creating these files, by the way, is bsave, and it works a little bit differently than the load. You have to actually give it some more information. So we can see here that our previous program ran from 0300 to 0310. So that is got a length of, what's that going to be? That's 16 characters? 16 bytes. Anyway, let's try that. Let's do bsave. We're going to give it a file name of high2. You do a comma for the next parameter, and we tell it we want to take address 300, then another comma, and we do L for length. We're wanting to do a length of 16 bytes. Let's see if that works. Let's cat that out, make sure that we got the file. Yep, high2, it's of type bin, perfect. Jump back into the monitor. Let's list what's currently in memory, great, okay. Then we're going to do 300 colon, and we're just going to give it a whole bunch of zeros. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then we're going to list it out again. There we go. So opcode 00 is a break, by the way. So I've just filled memory with a bunch of breaks. Actually, there's 311. I'll put 0 there, 0 there, 0 there as well. Okay. So we can see that we've zeroed out that memory there, basically. I didn't do 310. Not that it really matters. And if I drop back into here again, I'm going to do bload I2. Oops. Jump back into the monitor, decode 300, and boom, there we go. We got our program. So that's the kind of binary loading and saving commands that we have, as long as we actually boot off of a ProDOS disk, which is kind of handy. Is there anything else I wanted to mention? I think that's probably all the major stuff. Like I said, you've got a lot of capability here and so much access to the hardware. You can do a lot of really interesting things. But I think that's all I'm going to show you for today. So I hope you all enjoyed that. Take care, and I'll see you next time.